Hello, everyone. Welcome to the fourth webinar of our spring series. My name is Maria, and today I have the great pleasure of hosting this webinar with Professor Christine Aikens from Kansas University and Dr. Shana Havenridge. Now she's a postdoc at Argonne National Lab, but she was a PhD student with Christine. And they are going to talk about the work they have been doing, well, Christine for a long time and Shana during her PhD in collaboration with S-Adm, with Robert Ruger, who will be in a next webinar, about the implementation of analytical excited states gradients for TDDFT and type binding methods. Is now this method is implemented now in the latest release of AMS 2023. And well, whenever you want to start, Shana, the floor is yours.
Awesome, thank you. So I'm going to be talking today about the excited state gradients for time-dependent density functional theory plus type binding. And just to start off with just a little bit of background, kind of our main effort is trying to figure out photoluminescent mechanisms. And that's just because they're so important. They have, a vast number of applications from clean energy and electronics to biomedicine. And if we can, study these photoluminescent mechanisms and understand them more, then we can get to the point of making different materials and structuring them in a way that influences a particular application. And our group back at Kansas State University, we were really interested in noble metal nanoclusters. That's kind of our main goal and our main application was to look at these different nanoclusters and study them and try to understand what makes these structure property relationships. So if you change their shape, if you put different ligands on the around the core, they have different electronic structure properties. So you can kind of see that on the right over here, that when we change this, change the size of our gold, but keep the ligands the same, we see this change in optical properties. And so we want to come from kind of a photoluminescent mechanism point of view, and if we can understand the photoluminescent mechanism in these noble metal nanoclusters, they have these structure property relationships, we can tune them to different applications. And so how we usually do this is with TDDFT. And so I don't think I need to really describe TDDFT much for this audience, but just to be very particular in what we are looking at. We're looking at the linear response TDDFT, so we're looking at that kind of first linear order perturbation to our electronic density upon excitation. And particularly, we are using the Cassida approach. So, kind of where we have this eigenvalue problem set up, where we have our excitation and de-excitation vectors, and we're solving for our vertical excitation energy of our system. And so in these A plus B matrices, sometimes called rotational Hessians, we have all of our single orbital transitions that make these possible. And in this, we have our coupling matrix. And so this coupling matrix kind of couples these different single orbital transitions together. And as you can see, it's very complicated, right? These are very complex two electron integrals, and they take a lot of time to calculate. They're definitely the computational bottleneck of TDDFT. And so in 2016, kind of a pure exchange correlation functional approach was created kind of from the ideas of S2DA and S2DFT by Stefan Grumma. And that was the new time-dependent density functional theory plus type binding. And so essentially what happens is we use that Cassida approach, and instead of having this big, complex coupling matrix, make an approximation in the linear response regime. And so the new coupling matrix becomes this guy right here, where there's a monopole approximation applied to the transition density. And so this is made up of a Louvdine partial charge analysis, which is this Q here, and a chemical hardness parameter that's kind of based on this distance between the two atoms. And so this actually does a fantastic job at modeling these noble metal nanoclusters. As you can see, this is the cluster that is listed right here. And there's been some work outside of our group as well on these different gold and silver nanoparticles. And you can see that it really just does a fantastic job at reproducing the excitation spectra for TDDFT. And so it even does a little better than TDDFT+TB, which is in blue here. And that's because we are only making, this approximation is only made in the excited states, right? It's not made also in the ground state. So TDDFT+TB, excuse me, makes this approximation in the ground state as well. And so I think that's where we see a little bit of this difference come through. However, just making that in the excited states, it drastically cuts on the cost. So here's another example, and this actually isn't an artifact of the spectrum. We're actually calculating more vertical excitation energies with plus TB. And so TDDFT is kind of, the fit, the Gaussian fit that we have on our vertical excitation energies is making it cut down, but we actually have more vertical excitation energies calculated. So we can get that extra peak in the absorption spectra, and it really cuts down on the cost, right? So an hour on 16 cores compared to 25 hours on 22 cores. So really makes a big difference with these noble metal nanoclusters. The problem here, though, is that right before I started my PhD, we didn't quite have the analytical gradients. And so for problems like this gold-14 cadmium cluster, we still needed to use TDDFT to find our minima and our excited state gradients. And so this was with the collaboration, and they found that this cluster actually exhibited this rare dual emission. And so our kind of big question was, where is this happening? So when you do excited state geometry optimizations, right, it's very similar to the ground state. We're finding those local minima in our excited state, and or where the gradient is equal to 0. And so we're trying to find those, and it took quite a long time, but we eventually did find both emissive points in this large cluster. And it was actually a result from, doing an S1 optimization starting at the optimized ground state, and then optimizing the S2 and doing an S1 from an S2 geometry optimization. And we ended up finding both emissive points. But this took us quite a long time, right? It took over 90 days to find both emissive points that were kind of in the realm of experiment. And so, if you can cut 90 days down to, a month or so, it'd be great. But, and so that's, of course, was our ultimate goal, was to find a faster way to get at these photoluminescent mechanisms and understand what's going on in the excited states of these clusters. And so that's kind of what started my work. And so I have a Jablonski diagram here on the left. So we're trying to figure out, of course, this is electronic excited states. So we are looking at our kind of radiative pathways, right? It's we're not doing any dynamics, so we're mainly focused on this fluorescence, phosphorescence pathway. And just to kind of keep in mind, right, these aren't just lines on a diagram, right? They're very complex, multi-dimensional surfaces. And so we're trying to find our minima on these points. And so I'm going to go through, I'm not going to hit you with a bunch of derivation. I'm going to sum up the 4 main points of the derivation for you with what we did to come at this, this project. And so the first one, very similar to TDDFT gradients, TDDFT+TB gradients, MP2 gradients, a lot of different methods use what's called the Z-vector method or a Lagrange approach to come after the excited state gradients and get that. And so what we do is essentially start with a functional that represents our vertical excitation energy, right? We want to get at our excited states. So we want some kind of functional that represents that. And so in 2002, right, it was really laid out by, from the TDDFT gradients. And so using the variational approach, you can get a functional that looks equivalent to this, right? And we're very similar to TDDFT with the TDDFT+TB method, right? It's just replacing that coupling matrix and these rotational Hessians in this A+B matrix. And so ideally, right, we could just straight take the derivative of this with respect to the position of our nuclear coordinates and get an answer. But that would take a very, very long time. So the reason is because, of course, when we're doing our absorption spectra, when we're finding these vertical excitation energies, right, this kind of this like stick spectrum, this red is what we're finding. And, you know, of course, we'll usually set it to a fit to kind of look like experiment. But really, we're calculating these vertical excitation energies. And behind each one of those is a bunch of single orbital transitions, combination of them, and they're molecular orbitals, right? And so they are a combination of a bunch of different atomic orbitals, right? We have contributions, in this case, from our sp and our d and our sulfur, right? We have a bunch of different atomic contributions to these molecular orbitals. And so this makes the problem a little bit more complicated because then we would have to take the derivative with respect to every single molecular orbital coefficient. And we, of course, don't want to do that. So we go after the Lagrange method, the Lagrange approach, or a constrained optimization problem, kind of from a mathematical perspective. And so what we do is essentially add Lagrange multipliers. And these Lagrange multipliers restrict our functional to specific constraints. And so in our case, right, we want to restrict our kind of rotation of our molecular orbital coefficients. We want this entire functional to be stationary with respect to those. And so we take those kind of constraints and we plug them back in so that we can solve for our Lagrange multipliers. And so these are our constraints, right? So we want our entire functional, we don't want it to depend on those Lagrange multipliers. So we want our derivative of our z, which is one of the Lagrange multipliers, and our w, which is the other. And we want the derivative to be 0. We don't want it to depend on those. But then we want to apply our constraint, right? And our constraint is to restrict the transformation of these molecular orbital coefficients. And so we want the gradient with respect to those molecular orbital coefficients to be 0. We want it to be completely stationary. And so I'm not really going to go through this much. I'm just going to say, you know, then we just solve by plugging in our big L here, our big functional. We plug it in, we sum over mu and right multiplied by our coefficient matrix. And we do this simply to solve for our Lagrange multipliers, right? Because we say, hey, there's these Lagrange multipliers that exist that restrict this functional, but now we need to find exactly what they are. And so there's kind of, if you're interested, right, there's, in the supporting information, there's all of this derivation to find these Lagrange multipliers. But something I do want to mention is that this Z does contain the ground state kind of restrictions, and so it has the 2 electron integrals from DFT, whereas this W matrix has the nu plus TB approximation in it. So we kind of get this combination of stuff that from the ground state is, of course, does not have the approximation, and in the excited state does. And so with that, after you find the Lagrange multipliers, we just plug them back into our functional. And so then we take the derivative with respect to the position of our nuclear coordinates. And so we've denoted this here. So it's just each term, right? We're just taking the derivative of each term in our functional. And through some kind of mathematical manipulation, we can essentially get it down to this equation here, where we have a term that's dependent on our Fock matrix, a term that's dependent on our coupling matrix, and then of course the solution to our Lagrange multiplier W. And so kind of all in all, skipping through the derivation, what we have in the purple box here, this is what is implemented into the ADF code. So this is the final gradient for TDDFT plus TB. Like I said, this is a pure functional approach to the approximation. So we don't have any exact Hartree-Fock terms. And so these 3 terms up here form the derivative of our Fock matrix. Then the following 2 are the derivative of our coupling matrix, where you can see that Levene partial charge analysis is kind of coming through our square root of our overlap matrix. And then, of course, our solution to our Lagrange multiplier W. And so, yeah, so this is the overall gradient that's been put into the code. And this is, of course, like Maria said, it's available in the most updated release. It's in the ADF engine. And you can actually use pretty much a lot of the different properties you would use for regular TDDFT. Right? It was just kind of an added approximation. So you can run with and without scalar relativistic effects, with and without dispersion. You can use a variety of basis sets and GGAs, LDAs to do those calculations. It is available for singlet, singlet, and singlet triplet excitations. It's ongoing, but we have open shell excitations that's going on in our group to kind of get those triplet, triplet, or open shell excitations. So with that, I'm going to kind of talk about a little bit of our results. So after it's been implemented, we of course start off by testing the numerical versus analytical gradients. And we used TDDFT as kind of our benchmarking point. We're doing that opposed to experiment because, of course, this is an approximation to TDDFT. So it's been known for a while through several different articles. We know the problems and the benefits of using TDDFT versus experiment. And so we want to compare our method, that's an approximation to TDDFT, to it straight to see how accurate it is compared. So these RMS values that we have, so they are the difference between TDDFT and TDDFT plus TB. It is the emission energy at the optimized excited state. And so we tested 60 different systems, some diatomic molecules, and we took the smaller organic molecules from the teal test set, which just has a range of different, aromatic and non-aromatic, a bunch of different types of organic molecules. Our gold nanocluster core, because we wanted to test it out on just a bare core. Some ligand protected noble metal nanoclusters, and some molecular chromophores as well. And so as you can see, you know, the bigger our system gets, the better it works with this approximation, right? So most of our RMS values for our noble metal nanoclusters, our chromophore set, and our singlet triplet excitations in our chromophore set are actually less than 0.1 eV. Our organic molecules is a little bit bigger, but not too far off. We really have a larger difference with our diatomic molecules, but that's because the approximation itself, the +TB approximation, doesn't work very well for diatomic molecules. But you know, if you're running calculation on H2 or N2, right, I wouldn't make this method your top choice, right? You would want to go for TDDFT or something even more accurate than TDDFT if you're interested in those small systems. So really, really nice for big systems. And so then, of course, we do some runtime tests, and these are just kind of a handful of different ones. You know, we have a diatomic, a few from the teal test set, our nanocluster core, and then our one ligand protected noble metal nanocluster. And you can see that in all cases, right, +TB really cuts down on the time of our calculation, which is what we wanted. So yay, right, it's saving cost by making this approximation, but it drastically makes a difference in these noble metal nanoclusters, right? So we're optimizing our S1 state in 6 days compared to 17 days, right, with TDDFT. So you know, almost a third of the cost and a third of the runtime. So it's really nice to have kind of a faster method that you know, really gets very close on these emission energies. And so we don't just want to look at emission energies, right? We also want to make sure that we are finding the right minima in our excited state. So this is just a handful of different molecules again. And you can see that we really are obtaining this minima with both methods. So at TDDFT, the average bond lengths in angstrom are in red, and for +TB are in blue. Again, this is at the optimized S1 minima for this cases. And you can see here, really, we are just obtaining those bond lengths very well at our minima. And so that's really good to see. That means that, you know, we are obtaining that same minimum point. We're not finding another point that's maybe in a different local minima around the TDDFT minima. And so, yeah, so that's just kind of another good double check. So I did want this to be less seminarish and more webinarish. So I'm going to talk you through actually an example with gold 18. This has the ligand protected gold nanocluster that has 364 atoms altogether. And this is the average kind of bond length at the BP86 double zeta level of theory. Like I said, this code works with a variety of basis sets. You know, we tested TZP, DZP with, you know, different functionals as well, PBE, whatever you're kind of interested in that lies in that kind of pure exchange correlation functional regime. And so I just wanted to kind of show you a little bit. So if you look at my terminal here, right, so we can actually go, and this is kind of what the input file looks like with when you're wanting to calculate one of these excited state geometry optimizations, right? So we're not just calculating the absorption spectra, we're not starting at a single point and calculating all of our vertical excitation energies, right? We want a full geometry optimization of that excited state. And so, so our task is, of course, the geometry optimization, and you can use, you know, any of your keywords in your geometry optimization that you would like. This is just at the default convergence criteria right here. This is in the ADF engine, like I said, and so, you know, you can use you know, your any type of different functional you'd like. Wanted to point out that we're not doing it with frozen core, right? So we have the core none, right? So these are all atoms are accounted for in our full cores. We have our scalar relativistic effects here included, our SEF, our exchange correlation. Like I said, you can add dispersion in here if you'd like, and it runs fine with dispersion. And then we have these blocks are probably new, especially if you don't run excited state geometry optimizations a lot. So we want to add our excitations block. So this does our linear response. So essentially what we're doing is you're starting at a particular geometry, say your ground state, and we're calculating our vertical excitation energies, and then that's calculating the gradient, and it's saying, hey, is this gradient within the chosen criteria? Is it, you know, 0? And if the answer is no, of course, right, then it's going to move your geometry like it would in a ground state, and then it's going to calculate the linear response again. It's going to calculate the gradient, and it's going to do the same thing until you find that local minimum point. And so we do need our excitations in there. In this case, we're only doing singlets. And here's the main keyword. So this is what you would include for if you were doing a TDDFT+TB absorption spectra, for example. But now we're doing it with the geometry optimization. So we're simply adding that keyword into our excitations block when we do an excited state geometry optimization. And so, of course, then we have our excited go keyword, which stands for excited state geometry optimization. We're doing optimizing a singlet state, and we want to optimize our first singlet state. And so that's kind of the look of our input file. And if we kind of take a look at our output file here, right, you can find all of your same information, right? So we have our converged geometry, and, you know, prints it out for you where the geometry would be. You can look at your orbitals, you know, your overall orbitals, your HOMO-LUMO gap. You can look at, you know, specifically what's going on in your orbitals, the different contributions to your vertical excitation energies. And then, of course, you know, get your list of your excitation energies. So your optimized excitation energy at this new point is your emission energy, right? And so for this case with our S1 state for +TB, right, we get an emission energy of 1.16. And so this is pretty much exactly like the TDDFT input file, except for that one keyword where we have the TDDFT+TB included in there. And so after the optimization, of course, then you can print out an RKF file. And so I have kind of an example here. At that new optimized geometry. So on the left here, we have the ground state in our GUI, and on the right, we have our S1 state. So we can see, you know, you can look at your molecular orbital levels and see exactly how they change, right, upon excitation. So we definitely, you know, visually can see already that we have some big differences. You know, it looks like, yeah, it looks like these are on the same scale. So it looks like our LUMO is gaining energy, our HOMO is losing energy, right? We are kind of have differences in our orbital energy gaps now. If you're looking at like the LUMO and LUMO -1, right? We have a big difference in that energetic gap. You can look at that stuff. You can look at, you know, exactly what each orbital has in contribution of atomic orbitals. And then you can, of course, right, visualize them and see exactly, you know, how they change from our ground state to our excited state. Oops, wrong one. Let's go the right orbital here. Right, and so this would be like the difference between our homos, right? And so you can see for this particular cluster, right, we still have this kind of superatomic P character, which is what we would call what you kind of see in the middle here in the noble metal nanocluster community, where we kind of have a collective contribution of these atomic orbitals that are forming. You can kind of see this two-phase dumbbell shape in the core of our gold nanocluster here. And so you can see, you know, we definitely don't have too much differences between our S1 and our ground state for this particular cluster. But then you can look at, right, what makes up our photoluminescent mechanism, right? So if we look at our singlet state and we get some information on that singlet state, right, we see that we have a very, very large weight on this HOMO to LUMO transition. And so you can go into the GUI, right, and actually visualize, you know, this is our HOMO, right? And then if we look at our LUMO, we can kind of get an idea at what our minimum point is doing, right? And so we have kind of this P to D transition that's going on. So we have our, you know, our four-lobed D and the core of our nanocluster here, and our HOMO is very P-like, superatomic P-like. So we definitely have what I would say is like core-dominated emission or core-dominated fluorescence from this S1 state if it were to emit at this S1 state. So you can find out really cool information like that. And this matches TDDFT very, very well. So our, you know, our TDDFT results have an emission energy of 1.18 eV, but when you take the actual bond distances in the core, it turns out to be exactly the same. And this isn't an artifact, right? There is actually different numbers. It just comes out to be the exact average, which is pretty cool. That it just matches TDDFT really, really close, which is nice. But it takes less time, right? So for this particular example, it took half the time to run that +TB optimization. So kind of with that, I know this is probably a little bit shorter webinar. I just want to thank everybody who has helped me and supported me. Of course, my major professor with my PhD, Christine Aikens, is just amazing in all of the years. And I also want to thank Robert and Eric, who helped me a lot on the code. Robert completely did the parallelization of the code, and then Eric helped with, he merged the code into the trunk and found the last kind of bugs that made everything click together. And so I really can't take credit for this whole project without them. They were such great help. And of course, Stan for letting me, you know, go into the code and do some development, and my friend and old colleague Olivia for kind of helping me with some beginner code techniques, and then of course all of my present and past group members at Kansas State University. And so big thanks to everyone who's helped me with this project. And so with that, I'd love to take any questions or comments or anything that you guys have.
Thank you very much, Shana. Yeah, we have time for questions now, so please type your questions in the chat. I'm sure people will be very happy to be using this method that can reduce the time to half in some cases. Yeah, that's really good. Yeah, let me, I didn't mention, we attached the presentation to the handouts. So yeah, attendees can download the presentation from the handouts. Also, let me remind everyone that the next webinar will be in 1 week, no, will be next Thursday with Jochen Ausbach from Buffalo University. And in this case, it will be with Zoom, so no need for registration. You will still receive an invitation through an email tomorrow, just with the link to connect. So next week, same time, but on Thursday instead of Wednesday, you can directly connect to the next webinar. So we have now questions coming up. How can this method account excited states with charge transfer? Sorry.
Yeah. Right, we still have the same problems with DFT. Oh, here, I should probably X out of this guy. So we still have the same problems with DFT, and so you know, in itself, it does have some, it struggles with charge transfer, but you can get hints into the kind of excitations that we have kind of by using the GUI and looking at the orbitals that make up your excitation after your geometry optimization. So if, opposed to having, this kind of what we would say like core dominated here, let's say your excitation had more contribution between, say, like this orbital and a more ligand-based virtual orbital, right, that didn't have any electronic density in the core, right? So we have to keep in mind that, yes, we are still using pure exchange correlation functionals, but we do kind of get these insight and hints that, okay, at our optimized excited state minima, we do have this kind of electronic density that's not overlapping. So we do have some potential charge transfer in this cluster, or whatever chemical system you're interested in, right?
Okay, thank you, Shana. More questions? I hope, David, this answered your question. Now let's see, no more questions so far. We still have some time. Yeah, David says, thank you.
I tried to type in a question as well, but I'm not sure if you can see it. I can just ask it.
Yeah, I don't see any question from you. Yeah, maybe you can just ask it.
Good, yeah, so thank you, Shana, for a great presentation. I typed in a question, but I'm not sure it came across. So I'm wondering, of course, when you do excited state geometry optimization, sometimes you can have, as soon as you have a different geometry, that states can cross. And within the TDDFT gradients formalism, you can try and follow the eigenvector. As you start folding things into this Lagrange formalism, is there still a way in which you can sort of try and tag a certain excitation as you move from one geometry to the next?
Yeah, so it follows very, very similar to TDDFT, right? So where you're kind of following that particular eigenvector or that particular kind of state that you're interested in. So it's not going to switch states or anything. It's following, very, your dipole allowed states, your singlet, or whichever ones you're interested in states. So if you're interested in that singlet triplet state, it's going to follow that eigenvector kind of pathway, wherever it leads. But yeah, you're not going to cross states. It may TDDFT and plus TB as well kind of have this nice thing where they don't fully optimize when you're getting close to degenerate states. And so you kind of know that you are close to one of those where you're coming across a couple of surfaces that are getting close. So if you're optimizing like I don't know, an S5 state, for instance, just randomly off the top of my head, and you're optimizing, and as it goes along, your excitation energies in your output file are getting very close together, or it won't finish optimizing, and you know that you've kind of hit a degenerate state.
Again, I think to stress the fact that it has the same problems that TDDFT does. We're not going to be doing conical intersections correctly.
No, that's understood. Yeah, I'm just wondering. So some of these things you can try and sort of catch or find some resolutions for, but of course, yeah, conical intersections are pathologically impossible with TDDFT. Yeah, great. Another question, if I may. So now, of course, yeah, for your nanoparticle scalar relativistic will probably be good enough, but should there in the future be let's say spin orbit coupling formalisms also within the tight binding approach, would that be easily then implemented also in terms of excited state gradients?
Yeah, I guess I actually I haven't tested with the spin orbit coupling because that would be in the.
I don't think it works for just the vertical excitations, but I'm just wondering, should it be implemented? How much work would it be to then also update the gradients?
Ideally, I don't think too much. I know you can, because right now you can calculate your spin orbit coupling excitations, right? You would change your from a scalar Zora, right? You would have your spin orbit, and so you might get excitations that have like, you know, your 3-in-1 pattern where you kind of have your triplet singlet, and so I believe you would get the same, right? Because with plus TB, well, actually no, because you would have to specify that you're using the triplet hardness parameter. So maybe not, I'm not sure. I'd have to look into it.
Okay, maybe some future project.
Yeah, definitely.
We don't have more questions. If you have more questions, Fedor, right now. No? Okay, so yeah, I guess we can end now. Yeah, we are almost, yeah. So thank you very much again, Shana and Christine. I'm sure, as I said, yeah, people will find it very useful. And yeah, with that, I hope to see you everyone next week in the next webinar. So with that, thank you, Shana, Christine, and see you soon.
Yeah, thank you guys so much.
Thank you.
Thank you.
Have a good day.